Kirchhoff's law gives a fairly qualitative idea about the blackbody radiation and its consequences, but it failed to explain the dependence of the radiative power on wavelength and temperature. We have discussed the derivation of Kirchhoff's law and its importance in the previous video. In this video, we are going to discuss about the Stefan-Boltzmann law, the Wien's displacement law, and the Rayleigh-Jeans law. So without any further delay, let's get started. In 1619, Johannes Kepler put forward the concept of radiation pressure to explain the observation that a tail of comet always points away from the sun. Light, as electromagnetic radiation, has the property of momentum and thus exerts a pressure upon any surface that is exposed to it. This was published by James Clerk Maxwell in 1862, and it was proven experimentally by Russian physicist Lebedev in 1900 and by Nichols and Hull in 1901. The pressure is very small but can be detected by allowing the radiation to fall upon a delicately poised vein of reflective metal in a Nichols radiometer. Similarly, a thermal radiation trapped inside a cavity exerts pressure on the walls of the cavity. The pressure depends on the energy density of the radiation. Let us now find the expression for the energy density of radiation inside a uniformly heated enclosure of any shape at a certain temperature. Let V be a small elemental volume inside the enclosure and at a large distance from the walls. All the radiations inside V may be supposed to come from the surface of a sphere described about any point O inside V. The radius small r of the sphere is very large compared to the dimensions of V. Let the radiation from an elemental surface dA of the enclosure traverse along the radius to intersect V in a length small l. The solid angle subtended at dA by elemental area alpha is given by d omega equal to alpha by r square. The time taken by the radiation to reach the volume V is t equal to L by c, where c is the velocity of radiation. The amount of radiation contained in volume V due to the elementary cone is therefore given by this expression. Here k is the specific intensity of radiation, that is, the amount of radiation proceeding in a given direction per second per unit area per unit solid angle. The total amount of radiation contained in V due to dA is given by this formula. Integrating over all elements dA of the sphere, we get the total energy of the radiation in V due to the entire enclosure. So we find the energy density of diffuse radiation to be U equal to 4 pi k by C. Now, to derive the pressure which is exerted by this radiation, we consider a surface AB on which radiation is incident in a direction O with the normal to AB. The intensity of radiation in the enclosure due to the radiation coming from the direction enclosed in a small solid angle d omega is k d omega. We know from Maxwell's work that radiation pressure is given by the ratio of intensity and velocity of light. So pressure on AC due to radiation from theta phi is k d omega by c. Now force on AC will be same as force on AB. The normal component of the above force is k by c multiplied by d omega multiplied by AC cos theta. Pressure on AB due to radiation incident normally on it from theta and phi is therefore given by this equation. Integrating this over the entire hemisphere, we obtain the total pressure P of the diffuse radiation. But the energy density U in this case is given by 2 pi k by c. This happens because energy from one hemisphere is incident on AB, so the incident radiation pressure is given by this formula. But the dependence of total radiation from a radiator on its temperature was still to be found. In 1873, Joseph Stefan first showed experimentally that total energy of radiation emitted by blackbody is proportional to the fourth power of its absolute temperature. Assuming blackbody radiation behaves as a perfect gas, Boltzmann applied the laws of thermodynamics to radiation to deduce the Stefan law theoretically. The law is thus generally referred to as Stefan-Boltzmann law. It states if a black body at an absolute temperature T is surrounded by another black body at absolute temperature T1, the amount of radiation emitted per second per unit area of the former black body is given by sigma T to the power 4 minus T1 to the power 4. Here sigma is known as the Stefan constant. To derive this, let us assume U be the energy density of radiation in an enclosure of volume at a constant absolute temperature capital T and small p be the pressure of radiation. So the total energy of radiation in the enclosure is U equal to small u multiplied by V, where V is the volume of the enclosure. From the first law of thermodynamics, we know dq equal to du plus pdv. Simplifying and replacing the value of P by U by 3, we have this relation. Now, from second law of thermodynamics, we have dq equal to Tds, where S represents the entropy of the system. Replacing dq in this equation, we have the differential relationship between entropy, energy density, and volume. Now, according to partial differentiation, we can write ds like this. So by comparing the two equations, we have these conditions. As S is a state function, the second order derivative will be related in this manner. Now the temperature T is not a function of the volume, it only depends on the energy density. So the equation will look like this. Integrating the equation, we finally obtain log U equal to 4 log T plus log alpha. Here alpha is the integration constant and is called the total density radiation constant with units joule per Kelvin per meter cube. As the radiation Q lost per second per unit area of the enclosure is proportional to the energy density U, Q is also proportional to T to the power 4. Hence we have Q equal to sigma T to the power 4. This is Stefan-Boltzmann law where sigma is the Stefan constant. The constant sigma and alpha are related by this formula where c is the velocity of radiation. If you are interested in how this relation comes, you can check the description where I have provided links for further reading. Now when this body is surrounded by another black body at temperature T1, the latter will also emit radiation equal to sigma T1 to the power 4, which will be incident on the first body. So the net loss of radiation of the first black body per second per unit area will be Q equal to total energy radiated minus total energy absorbed, which is sigma multiplied by T to the power 4 minus T1 to the power 4. Stefan's law was put to experimental tests by Lummer and Pringsheim using the total radiation from a black body over a wide range of temperatures from 100 degrees Celsius to about 1300 degrees Celsius, and it has been well verified. Stefan-Boltzmann law shows how the total energy of radiation is related to the temperature of the source of radiant energy. But the emitted radiation is not confined to a single wavelength. Instead, it is spread over a continuous spectrum. So the immediate question is how is this total energy distributed amongst the different wavelengths? The attempts to find an answer to this question constitute a long and painstaking history of growth and development of physics. The first step in this direction was taken by Wien in 1893. He showed that the spectral distribution of energy emitted by blackbody at a temperature T can be expressed by this, where U lambda d lambda is the energy density of radiation between wavelength lambda and lambda plus d lambda. This is known as the Wien's law of energy distribution. Wien also showed that if radiation of a particular wavelength at a certain temperature is adiabatically changed to another wavelength, then the temperature will change in the inverse ratio. That is, lambda multiplied by T is a constant. This relation is known as Wien's displacement law. We are going to derive Wien's displacement law purely from thermodynamic consideration. Let us consider a spherical enclosure with perfectly but diffusely reflecting wall capable of moving slowly outward. Let the enclosure be filled with black radiation characterized by thermodynamic temperature T. Now, the enclosure is allowed to expand adiabatically by supposing its walls moving out slowly with a small uniform velocity V. Due to the reversible adiabatic expansion, the temperature T will fall to T prime, but it can be proved thermodynamically that the quality of radiation will remain unaffected. To understand why it remains unaffected, check the link in the description. Although the nature of radiation will not change due to expansion, the wavelength will get altered due to Doppler shift on each reflection at the moving wall. Now, for normal incidence, a particular wave of length lambda changes by Doppler shift for each reflection to lambda prime. When the incidence is at an angle alpha with the normal, the resolved part of V along the direction of the ray is effective in changing the wavelength. So for oblique incidence, we have this condition. For a narrow beam incident on the boundary of the spherical enclosure at B making an angle alpha with the radius at B, the angle of reflection, however, will be different from alpha, since the walls reflect diffusely. If the ray starts from A at time t equal to 0 and S1, S2, S3 are the lengths of the chords travelled by radiation between successive reflections in unit time, we have this relation, and cos alpha equal to S1 by 2r, cos beta equal to S2 by 2r, and cos gamma equal to S3 by 2r, and so on. After the first reflection, lambda is given by this formula. And for n successive reflections, we need to multiply the Doppler term n times. Upon approximation, we get lambda f equal to lambda multiplied by 1 plus v by rc into summation over si. This gives lambda into 1 plus v by r. The lambda f is the value of wavelength after unit time has passed. So lambda f minus lambda can be replaced by d lambda dt, and v can be replaced by dr dt. With this we obtain d lambda by lambda equal to dr by r. On integrating this equation, we obtain lambda by r equal to constant, or lambda cube by v is equal to constant. Since the amount of energy we started with is now distributed over a larger volume and a part is spent in doing external work, the temperature of the enclosure will change. The process being adiabatic gives us du plus pdv equal to 0 from first law of thermodynamics. Here du is the total change in the internal energy and pdv is the work done by the radiant energy. But u equal to small u multiplied by capital V and P is equal to u by 3, where u is the energy density of the radiation. This gives d of uv plus u plus dv by 3 is equal to 0. On simplification, this gives du by u plus 4 dv by 3v equal to 0. But from Stefan's law, we get u equal to a t to the power 4 and v equal to 4/3 pi r cube. Plugging these in the previous equation, we yield dt by t equal to minus of dr by r. Combining the equations, we have d lambda by lambda equal to minus dt by t, and on integration, this gives lambda multiplied by t equal to constant. Thus, if radiation of a particular wavelength at a given temperature adiabatically changed to another wavelength, the temperature changes in the inverse ratio. This is the Wien's displacement law of radiation. It can be shown that the results will hold good for an enclosure of any shape, not necessarily restricted to the spherical one. Now let us move to Wien's distribution law. The work done in adiabatic expansion by the radiation of wavelengths between lambda and lambda plus d lambda is p lambda multiplied by delta V. Here p lambda is the pressure due to radiation of wavelength between lambda and lambda plus d lambda. So this is equal to u lambda multiplied by d lambda by 3. Now this work done must be equal to the energy reduced during expansion, which is given by delta of u lambda multiplied by d lambda into V. So from this we have the following equation. Dividing each side by u lambda d lambda V, we get this. We can always prove that delta lambda by lambda equal to delta of d lambda by d lambda. Again, if you want the proof, check the further reading in description. Now replacing V by 4/3 pi r cube, we get delta r by r equal to 1/3 of delta V by V. And we just recently proven that delta r by r is equal to delta lambda by lambda. So our final equation looks like this, and by integration we obtain this relation. Plainly, u lambda is a function of t, so the constant must involve t. But for this process we know lambda t is equal to constant. So this constant is a function of the product of lambda multiplied by T. Finally, the equation should look like this. Wien suggested the function f lambda T from the analogy of Boltzmann energy distribution. So the final form of Wien's distribution law looks like this. But this was as far as Wien could go without knowing anything about the actual form of the spectrum. In the later years, experimental results showed that Wien's distribution looks very well in the smaller wavelength region, but it fails in the larger wavelengths. In the light of the failure of Wien's radiation law to account for the experimental results at longer wavelengths, Rayleigh and Jeans approached the problem differently and came up with what is known as Rayleigh-Jeans law. The Rayleigh-Jeans law of spectral distribution of black radiation is derived on the basis of two theorems. One, the theorem of stationary waves in a hollow enclosure, and two, the theorem of equipartition of energy. The blackbody chamber is filled with diffuse radiation of all frequencies between nu and nu plus d nu. This radiation is composed of EM waves in space. They are reflected time and again from the walls, forming stationary waves in the space of the enclosure. Rayleigh showed that the number of vibrational modes for frequency between nu and nu plus d nu per unit volume is equal to 8 pi nu square d nu by c cube. If you want a detailed derivation of this, check out the description. Once this is established, the distribution of energy can be derived by the principle of equipartition of energy. Considering the kinetic and the potential energy, the total energy of each vibration will be kBt, where kB is the Boltzmann constant. In terms of the wavelength, equation becomes this. This is the Rayleigh-Jeans law of spectral distribution of energy. The laws of thermal radiation, as reduced theoretically from classical principle by Wien and Rayleigh-Jeans, however, failed to interpret the experimentally observed energy distribution amongst the different wavelengths of black radiation. A deeper look into the Rayleigh-Jeans law gave something known as ultraviolet catastrophe. In the next video, we will discuss more about this and how it was solved by Max Planck, which resulted into the birth of quantum mechanics. Thank you for watching. I hope you liked it. Please like and share this video, and to see such videos in future, do subscribe.